Okay, so in this video, we're going to take a look at a couple of rules, a few rules for probability. Right now, the first one is the complement rule, similar to when we are counting. Sometimes it is easier to find the complement and then just work from there. Uh, so here, the idea is that the probability of the sum of all the probabilities is 1 or 100%. Right? So the idea here is that the complement of the event, so here, the complement of an event E, and it's written, they use this little bar over E. Certain textbooks, sometimes if you're looking at other resources, you might see E to the C like this as a complement. And this is to signify is the event E does not occur. So you can just think of it as a binary situation, right? If you have an event E that occurs with some probability, and it does not occur with another probability. Right? But in other words, right, if we just kind of think of our sample space as event E and event not E, the complement, then the sum of these is equal to 1. So either the event happens or it doesn't happen, right? So it has to add up to 1. And here, doing a little algebra, the probability of E is 1 minus the probability of, excuse me, probability of the complement is equal to 1 minus the probability of E. Right? Because if we just kind of think of the sample space as either E and not E. Right? And again, it's usually helpful here to calculate this when the sample space is just easier to count than the event itself, right? Okay. All right. So, for example, let's say we were to flip a coin. All right. Again, we'll assume it's a fair coin. Flip a coin 10 times. And I want to find the probability of getting at least one head. Of getting at least one heads. All right. Now, if I wanted to do that, we would have to calculate, well, one of them is a heads, two of them, three of them, etc. But what if we just instead focus on the complement, right? So the equivalent idea of doing that, right? Instead of going here, so we can think of the probability of at least one heads, probability of one heads plus probability of two heads, etc. All the way. What if they were all heads? 10 heads. Right? We would have to calculate each one of these individually. Right? But if we instead think of a complement, well, either you have at least one head or you have no heads. And it is much easier to calculate. That's exactly one way that could happen if you get a string of 10 tails. So alternatively, you could say, well, 1 minus the probability of no heads. Right? That happens exactly one way out of 2 to the 10 different outcomes. All right, and then just simplification, that's 10 to the 24th. So we get 1023 over 10 to the 24th. All right, okay. So that is the complement rule, right? Again, here, if you find yourself in the situation where you're doing calculations and you're like doing from 1, 2, etc., stop and think to yourself, well, maybe I can just use the complement, right? What would be this not happening, and take it from there. Right. Another rule we have is the addition rule. All right. And really this is the same idea as the principle of inclusion-exclusion, but for probability. Right. Now, if A and B are disjoint events, right, A and B, then the probability of both happening is simply the probability of A plus the probability of B. All right, now if they overlap, right, then here simply doing as above is as overcounted, right? Probability of A plus probability of B. So you have to subtract the probability of A union of B, because that has been counted twice. All right, so let's say that the example was you roll a six-sided die. All right, let A be the event that it's even, and B be the event that it is less than 3. Okay, so again, the sample space for rolling the die are the numbers, it's one die, so 1 through 6. So that is my sample space. Each of these equally as likely, right? So just 1 through 6. Okay. All right. Okay. So the probability that it's even, that would be 2, 4, 6, so 3 out of 6, or 1/2, so half of them. The probability that it is less than 3, all right, now again, make sure we read that carefully. Less than 3 is just two values, 1 and 2. So that's 2, 6, which is 1/3. Okay, now if you want to find this probability, the probability that A is even union with, so n less than 3, B. So again, we can start off by just can write out the formula. A union B, right? Now, if they are disjoint, what you'll calculate is that last term is 0, right? So it reduces down to A, probability of A plus probability of B. So probability of A is 1/2, probability of B is 1/3. And if we look at which one is even and also less than 3, well, that will be 2, exactly one of the outcomes. So that would be minus 1/6, which when you combine all these together, we get 2/3. Okay. All right. Now, lastly here, we have this idea of independent events. All right. And if I have two events, A and B are independent. If the intersection, A intersection of B, the probability of both things happen is probability of A times probability of B. So again, this is analogous to the product principle, just in terms of probabilities. Right? The way you think of it when we are talking about probabilities is that one event gives no information about the other. Right? So, for example, let's say we're talking about rolling a die. Roll a die. And we'll call event A. You get a multiple of 3. And flip a coin. B. You flip a heads. All right. So in this case, if again you're kind of playing a game and you're doing these two things, rolling the die, flipping a coin, right? So what's the probability of A intersection B happening? All right. Well, again, these aren't. We do these separately. So the probability of rolling a multiple of 3, so that would be 1/3, right? We get either 3 or 6, and then times 1/2, so we get 1/6. Both of these happening. Okay. Okay. Now, in contrast, what is not independent, so let's say you picking random cards without replacement. Okay. All right, so if you pick any card, right, so pick let's say the probability that you pick the ace of spades. All right, so the probability of that happening, right, that would be just 1 out of 52, right? That's always just one particular card here, right? Let's say the probability that you pick the four of clubs. All right, and then that's also 152, 1 out of 52. Okay, now this is, if you just think of these individually, you have the 52 cards, you pick one, and that would be your probability, right? But what if you were to do these consecutively, right? What would be the probability of getting a spade first, all right? A, you're picking 2 cards, so A, ace of spades, and 4 of clubs. Right, and again, here this is without replacement. So once you pick the first card, you don't replace it back, right? So in that case, right, the first one is still the same, 1 over 52, right? But now the next one, you've slightly increased your odds if that happens, right? Because then it's 1 over 51, right? Still the product principle, right? But it's not the same because there's one less card in the deck, so we have to adjust our sample space. All right, so just keep that in mind here, right? It's important how we run the experiment, right? And that'll give us a clue as to whether it is indeed independent or not.